I'll be talking about inelastic scattering of a photon by phase slips in a small superconductor. And here's the outline. So I'll first introduce actually a spreading qubit transmon. And then I'll discuss how a Josephson junction array can be used as a waveguide for microwave photons. And the combination of the two actually allows one to do something quantum optics, some down conversion of photons. And then I'll discuss how it can be used to see some unusual microwave fluorescence in this kind of device. So, so first of all, what is a qubit? Essentially, it's a small Josephson junction, and its Hamiltonian consists of two parts. So, first part is just Josephson energy; it's well known. But if it's small, also, then another term is important. If I tunnel two electrons, a Cooper pair, through the junction, I'll have some charging effect, and it will bring the just charging energy q squared over 2c. So these are these two main terms. Now, this q and phi are non-conjugate, are non-commuting variables. They basically, it's like an angle and angular momentum in quantum mechanics, the same commutation relations. And we can just, in phase representation or in coordinate representation, if you wish, you'll get a simple Hamiltonian with periodic boundary conditions. So system is confined and spectrum is discrete, right? There is one more component to the system, which actually not always pleasant, polarization charge. So just imagine that there is some battery and capacitively coupled to the junction, and I can just induce some polarization across the junction. Okay, that will shift this charge q hat by n. So this way, actually, the energy spectrum levels depend on this parameter. Now. The terminology. So, charge qubit is a qubit with small Josephson energy compared to charging energy. Transmon is opposite limit when charging energy is small. And actually, this is the workhorse of all the working. Basically, industrial quantum computers. You'll hear perhaps more about it from one gal on Friday. So basically, transmons are in all these fancy things. And paraphrasing what yesterday's talk, Matteo Paris was telling that the transmon basically is almost harmonic oscillator. And microwaves, although it's low frequency, but still being quantized as photons. So in this respect, it's kind of typical quantum optics setting. Now, in the Kurdos approximation, basically, we can replace a minimum in this cosine potential by an harmonic oscillator potential. And in this case, there is no tunneling between the minima, and therefore the energy levels are still not equidistant because it's an harmonic oscillator, but the levels are independent of the displacement charge. And that's actually the limit that people like in industry. So that allows qubit to be stable. But if we have a non-perfect qubit that allows tunneling of phase, then the tunneling of actually the amplitude of tunneling depends on the displacement charge, and therefore it brings the dependence of energy levels on the charge, and the higher the level, the broader is the dispersion of the level with the charge. So it's exponential, but it grows with the level. Exponential is the parameter j over c. Now, can we allow n to be a quantum variable? Can we give it quantum dynamics? Actually, yes. So for that, we can remove this battery and attach a transmission line to the qubit, okay? And then on a classical level, we can just vary charge the displacement charge harmonically, and there will be some resonance at the transition frequency E1 minus E0. Now, at the next level of sophistication, we can also allow some quantum fluctuations, and in this case, the incoming classical light will create entangled photons, and the minimum number of photons is 3 just by time reversal symmetry. Now, in the next level, basically, n is a quantum operator, and we can try to spontaneously parametrically down convert the incoming single photon. Okay, so It turns out actually, and that's the key of our work, is that the spectrum of the down-converted photons crucially depends on the transmission line impedance. So now, with impedance, it's easy to make a transmission line with low impedance, and it's pretty hard to have a high impedance. But it's possible to do with a one-dimensional Josephson junction array. So basically, this thing characterized by three parameters, three energies: the Josephson energy, the charging energy of the Josephson junction, and yet another charging energy with respect to the ground. So each island, specific island, has some coupling to the ground, and there's yet another energy, Eg. And it's quite straightforward, turns out, to arrange conditions when these junctions are almost classical. So there are no phase slips. Ej is much larger than Ec. However, this charging energy to the ground is order of Ej. So in this case, basically, this array of nonlinear elements works as array of linear elements, and waves can propagate like plane waves along just harmonic waves along this array. And it's actually is done. It's more than 10,000 junctions, and Q factors are fantastic. So that's basically dissipationless waveguides with very slow light. And respectively, the impedance is very high. So impedance, if Ej is order of Eg, then this is order of 1, and the impedance is quantum unity, 6.5 kilo ohms, which is way greater than vacuum impedance, about 400 ohms. So again, it's because of the matter-light connection. Photons are basically the quantized waves of charged superconducting condensate propagating along the array. Now, so this way, basically, this kind of mute n becomes an operator because this is the charge delivered by these waves to this junction, okay, n hat, and we can expand it in the creation annihilation operators of photons. Now, this expansion coefficients actually depend on the impedance. It's just a straightforward textbook exercise, so it's proportional to 1 over square root z. Now, back to calculation. So, as I said, the lowest number of created photons is 3. So one photon can be down converted to 3. And what is non-trivial is that there is a contribution to this process which is singular in 2 of the 3 outgoing photons frequencies, 1 over omega 2, omega 3. This singular contribution is special. It comes only because these levels disperse with charge. And they disperse with charge because of these phase slips that I was already introducing before, because the phase can jump from one junction from one minimum to another. And it's very different from conventional kernel linearity that comes just from nonlinear oscillator terms like phi to the fourth. It will not be singular this way. So this is perturbative result, and there are differences between these frequencies. So it's convenient actually to focus on this relatively high frequency photons that goes out and integrate over the low frequency photons, and look at the inelastic cross section of scattering of the initial photon into this omega prime. So this guy is lower frequency. It's inelastic scattering, meaning that something just goes to the photons that we integrate over and we don't care about them. They just left. Okay, so the scattering cross section is still singular at omega equals omega prime. So perturbatively, you see that the scattering is kind of very soft. Now, if you go to higher orders, uh, you may emit more photons, and turns out that one of them is high frequency, others are lower frequency. And there is a way to collect the series to all powers in 1 over z. I will not discuss how to do it, but the result is that this perturbative parameter now is promoted to the exponent. And the non-perturbative result for this inelastic scattering from omega to omega prime is proportional to 1 over omega minus omega prime to some exponent, which knows about the impedance of the transmission line. That's why I was telling that impedance is important. Now you must, okay, whether this dichotomy is really working, and the answer answer is it is working, but only if Z is larger than RQ. So one needs this high impedance transmission line to allow this result to hold. And in this case, actually, this distribution is normalizable. So indeed, the majority of photon, well, the majority of inelastic process occurs in a soft channel, so to speak. That the scattering occurs only with small energy loss. Uh, so, so that would be nice to see. But what was done in experiment by a group of Manu Charan at that time at Maryland University was a bit simpler. So, so this is what we would like to see. But what they were able to do is to shine photons at resonance and look at the total cross section of resonant fluorescence. So basically integrating over all the outgoing frequencies, including omega prime. So for this quantity, on the other hand, we can just have the full result depending on all the parameters. So here we know everything, including the dependence on the resonant frequency. So in experiment, actually, they were able to change the resonant frequency because somebody mentioned, well, Bristock mentioned fluxonium. So it was a simpler qubit. It was just a squid, but it allows by flux changing the resonant frequency. So they were able to change frequency of the qubit, and all parameters are more or less known. And so we could calculate with the accuracy of experiment what we expect for gamma, and it's more or less agrees with the experiment for several devices, which progressively go closer to Z equals RQ. So that's basically the core of my talk. So I would like to finish with the I think I'm fine on time, right? With some outlook and explaining why we care. Uh, so, as I said in the beginning, an enchanted transmon, and again, it's a lousy transmon, charge sensitive. It's not what is used for the practical purposes. But in this charge sensitive transmon, phase freely tunnels between the classical energy minima. Now, for high impedance transmission line connected to the transmon, okay, it inhibits a little bit tunneling, but still phase is still able to tunnel between the minima. Now, it turns out that if you take Z less than RQ, then the phase gets localized. So there is no way to tunnel between the minima if you attach a line with Z less than RQ. And this is the essence of so-called Schmidt transition that was discovered, theoretically discovered by Schmidt back more than 40 years ago. Remarkably, experimentally, it's still debatable, and nobody kind of confirmed it clearly that its existence. And basically, this quantum optics approach, just looking at the inelastic scattering of photons, in our view, gives some another pathway to see to observe this transition. And we developed a full theory of it. You can look at the paper. Thank you.
Thank you very much. Yes, please. We have questions.
Thank you for very nice talk. Please, let me ask a question. You have started by saying that this transmon is like harmonic oscillator. I'm asking, why are you not calling quantum rotor? Because sometimes you are using, let's say, harmonic oscillator, but there is just a single frequency. But quantum rotor is something different. It's something what includes this anharmonicity. And it's described by their own complementary variables, not just XP, but this angular momentum and exponential operator. Do you see any differences, really differences between harmonic oscillator and this transmon?
So the difference between harmonic oscillator and transmon.
I'm saying that it is quantum rotor, and quantum rotor is not harmonic oscillator, and quantum rotor is not a two-level system. But in this terminology, I understand that you are using it. That probably you are satisfied with this kind of approximation.
Right. Yeah.
But
so
basically, it is one of the fundamental systems with their own symmetry, own, let's say, quantum formulation, quantum phase space formalism, whatever.
Well, you are right. In principle, you are totally right. And this is the difference between having compact and non-compact, and one minimum or many minima. But the thing is that for why people call it anharmonic oscillator, because they suppress tunneling so much that you are sitting at one minimum, and that's why actually the devices work. Okay, so yeah, sure.
Are there any further questions?
Thank you for the talk. Can this be used to create multiple photon fog states on demand? The soft photons?
Right, so that is possible, but not with what I am telling. So basically, for multiple photons on device, people do use, basically they use Kerr effect. So you put a qubit in a cavity, and then if you properly tune their frequencies by Kerr, you can create photon pairs, for example. So this is something that people in circuit QED, which is microwave version of cavity QED, people do it.
Okay.
There's another question there.
There is one last question.
Would you explain how the N can be operator?
How the script, this one?
Yeah, at the later slide.
Right. Yeah. So that's very simple, because basically this N becomes here. This N is basically charge delivered by the shift of the charge along the Josephson chain. Okay, and because this charge can be expressed in terms of the harmonic oscillations of the charge in the system. So that's basically how it becomes an operator. It's harmonic system, so it has conventional waves. Okay, it's waves of matter, but it's still waves, and you can quantize them. It's like photons or phonons or any other linear wave.
Thank you.
Okay, let's thank the speaker again.